This review will cover what derivatives and integrals are, and it will also cover how to take derivatives and integrals of functions that we will commonly encounter over the course of our 2 semesters of PChem. So I want to start off with a review of what derivatives and integrals are for those of you who haven't taken calculus in a while. So let's start with a function y equals x squared, so a simple parabola. You probably remember how to take the derivative and integrate this function, but I want to go through this as an example of what derivatives and integrals are. So recall that the derivative, if we want to take the derivative of this function, I'll put a d here for derivative. The derivative is simply the slope at every single point along our function. So if we wanted to, we could take the slope here at x equals 1 and find out that that is equal to 2. And so we could put a point here at 1, 2, and we could do the same thing for x equals 2 and find that that slope is equal to 4. And so we could put a point here at 2, 4. We plot this, we get a line, and this is our derivative of our function x squared. In this case, it's 2x. We can do the same thing here. So if we take another derivative going this direction, we can find the slope at every given point along this line. And what you'll discover is that the slope at every single point is going to simply be 2 because it's just a line of x equals 2, y equals 2x. So that's going to give us y equals 2 as our derivative of 2x. Now, the integral can be thought of as going in the reverse direction of the derivative. So we'll see that if we take if we integrate the function y equals 2, we'll end up with a function of y equals 2x. And we can also think of that as getting the area under the curve. So we want to get the area under the curve here. So if we again go to our point x equals 1, how much area have we covered by the time we get to x equals 1? Well, we have a 1 by 2 rectangle, so we've covered an area of 2. So we would plot the point here of 1, 2. And if we go to x equals 2, we've now covered an additional 2 units of area, so that would be a total of 4. So we plot the point 2, 4. And again, we can do this and construct the line y equals 2x, and we could do the same thing to y equals 2x and come up with the function y equals x squared. So just as a recap, right? So derivatives are can be thought of as taking the slope at every single point, and integrals are finding the area under the curve. And these are kind of opposite each other. So there are a few functions that we'll see over the course of physical chemistry that you want to be able to integrate and take the derivatives of relatively easily. And the first of these is polynomials. And we've just seen an example of how to take the derivative and integrate polynomial functions, but I'll go through a specific formula for this. So if we have some function x raised to the n, and we want to take the derivative of it, what we need to do is take our n, our exponent, and bring it down and make it a coefficient to our polynomial. And then the exponent number, as we've seen, gets reduced by 1. So if we have x raised to the 2, we bring the 2 out front, and then we have x raised to the 1. So for example, in this case, if we were to take the derivative of x to the n, an arbitrary polynomial, we would end up with n x to the n minus 1. And we could keep taking the derivative. If we wanted to take another derivative of this function, I spelled derivative wrong. If we want to take another derivative, we would end up with n times n minus 1, right? And then we'd have x to the n minus 2. And if we want to integrate a function, x raised to the n, it's an opposite process. So if we have x to the n, what we want to do is end up adding 1 to this function to integrate, and then we need to divide by x to the n plus 1, or multiply by 1 over n plus 1. And you can see this is going to be the opposite of what we're doing before. So if we integrate this function x to the n, we end up with 1 over n plus 1 times x raised to the n plus 1. And we can do that again. And we would get 1 over n plus 2, n plus 1 times x to the n plus 2. And so if you are not convinced by this, you can go through and play around with this and find out that this process of integrating is the exact reverse of the process we did above, taking the derivative. So for some examples, let's look at the function x to the 5th. If we wanted to take one derivative of this function, we would end up with 5x to the fourth, just following the same process that we did above. And we could take a second derivative and end up with 20, which is 5 times 4 times x cubed. And now if we were to integrate, so let's say we wanted to integrate 5x to the 4 here, well, we need to increase our 4 by 1, bringing it up to 5, and then divide our x by 5. So we'd end up with 5x to the 4 times 1 over 5, which is just simply back to x to the fifth. And if we wanted to integrate x to the fifth, we could just do the same thing, and we end up with 1 over 6 x to the sixth. Sometimes when you're taking integrals, you'll end up with, in derivatives, you'll end up with a series of polynomials. And if we have that, we just take the integral and derivative of each polynomial separately. So let's say we have something like 1/2 x to the fourth plus 7x. If we wanted to take the derivative of this, we would just take the derivative of each part of this polynomial separately. So if we were to take the derivative of 1/2 x to the fourth, that would give us 2x cubed as we bring down the 4 and then switch the 4 to the 3. And then the derivative of 7x would just be 7. If we wanted to integrate this function, we would just, again, integrate each piece separately, and that ends us with 1 over 10 x to the fifth plus 7/2 x squared. So I encourage you to go through, and there'll be some practice problems posted to practice this if you want to get a refresher on how to do simple derivatives and integrals. The next thing I want to cover is trig functions. So we'll see trig functions a lot in physical chemistry, specifically in the form of sine and cosine waves. So you probably remember from Gen Chem or AP chemistry in high school, or maybe just chemistry in high school, that there's something to do with wave-particle duality or particle-wave duality, and that's going to be a major topic of physical chemistry first semester quantum mechanics. And so when we're talking about particle wave duality, what we'll encounter a lot is sine and cosine waves. So let's start by looking at a sine wave here. I'll do my best to draw one, but a sine wave is a function that starts at 0. It increases to a maximum of 1, then decreases back to 0 through pi, hits -1, and then goes up to 2 pi, and then continues on in this wave form. And it'll go on indefinitely. So just like polynomials, we'll want to be able to easily take the derivative and integrate these functions. I'll go through a quick example of how we do that. Again, we're going to use the same property that we did before, specifically on the derivative. So the derivative of a function is just is the slope at every single point along that function. So if our function here is sine of x, and we want to take the derivative, we simply need to calculate the slope at every point. And so we can do that, and I'll go through what this looks like, and you can believe me or check it on your own if you want. But what you can see here is that at this maxima and minima up here, the slope is 0. So that means when we're taking the derivative of sine of x, we should be going through 0 at the maxima and minima. And also at this point, the slope is maximum at 1, and here the slope is maximum at -1. So we'll want to be hitting this point and this point as well. And as we go through, the slope is constantly decreasing to 0 and then increasing to -1 and then going back to 0 and 1. So if we were to construct this function by taking the derivative, we end up with this shape. Now, if you remember your trig, this is exactly a cosine curve. So just by taking the slope at every given point, we end up with the derivative of sine being cosine of x. And we can do this a few more times. And if you remember back to calculus, if we take the derivative of cosine of x, what we end up with is negative sine of x. And then if we take the derivative of negative sine of x, of course, we end up with negative cosine of x. And then we get all the way back to sine of x when we take the derivative of negative cosine x. And integrating these functions is, of course, just like we saw for polynomials, just in the opposite direction. So if we wanted to integrate cosine of x, that would end up with sine of x, so the integral of cosine x. is equal to sine x, just the opposite direction of our derivatives. And so the next function that we'll see a lot in physical chemistry is exponential functions. So we'll be dealing a lot with exponential decay. So you probably are familiar with exponentials before. So an exponential function is something of the term e raised to the x, where e is a number. It's like pi. It's a number that's approximately 2.718. It's all on your calculators. You just use this number e, and it at some points over the course of the semester, we'll need to be careful to distinguish this E, this Euler's number, from the E, the fundamental charge of an electron. And sometimes they'll come up in different situations, and sometimes they'll come up in the same situation. So just be careful to know exactly what's going on when you're solving problems. And this, if you're curious, this number E comes from the number where the natural log of this number is equal to 1. So that's the origin of this number E. And so if we wanted to take the derivative of our function e to the x, well, it ends up that the derivative of e to the x is simply e to the x. And in the same way, the integral of e to the x dx is simply e to the x as well. The last function that we're going to want to be able to specifically integrate is the natural logarithm. And this will come up in the second semester, so we won't see this too much in the first semester, but it'll come up a lot in thermodynamics. And so logarithms, just to give you a quick review of logarithms, are kind of the undoing of exponential functions. So for example, if we were to take 2 and raise it to the 5th power, this would give us 32. And if we wanted to undo that, we would take a log base 2. So we could take a log base 2 of 32, which is the same as taking a log base 2 of 2 to the 5th, and that ends up equaling 5. So the natural log is simply a log base e. So if we were to take a log base e of e to the 5th, we would typically write that as natural log of e to the 5th, and that would give us 5 as well. And we'll see this next semester. What we'll encounter a lot is ending up needing to integrate the function dx over x. And when we integrate this function, this ends up being the natural log of x. So if we were to want to take the derivative of natural log, this would end up with 1 over x as well. So I'll just write that. So d dx of natural log is equal to 1 over x. So these are the most common forms of integrals and derivatives we'll see over the course of our year together. We'll see some more advanced ones, but you won't need to be able to solve more advanced ones. But being familiar with these simple forms, so polynomials, trigonometric functions, exponentials, and then natural logarithms for next semester, being familiar with those simple maths will help us when we encounter more complex problems.